Well, hello, this is Ron, and this is Mechanics of Materials. And we have our first video on bending loading. So, with all of our different loadings, axial, bending, shear, and torsion, um, we have the fundamental concepts of load, stress, deflection. In some cases, we have strain. This is bending loading is one where we don't. And uh, with bending, we'll first look at the different ways that it's loaded. Then I'll show you the equation for stress. And then we'll talk about deflection. So here's a handout that you'll be getting in class. And it has a wide variety of different cases of loading in bending. Turns out that it's also for loading and shear. So here in case 1 we have a cantilever with an end concentrated load. So we have a fixed support on the right, concentrated load on the left. Here we have a fixed support on the right and a distributed load. Here we have a fixed support on the right and a triangular distributed load. Here we have a fixed support on the right, a hinge support on the left, and distributed load. And there are many, many different potential loadings, many different cases. I think we have 16 or so. Here's a case where we have a fixed support on the right, but then instead of being loaded with a force, we're loaded with a moment. So there's a concentrated moment at the left end. Here is a very typical loading, one of the first ones we learn about in statics, where you have simply supported on the left and the right with a concentrated, just one concentrated load in the middle. Well, let's zoom in here if I can do that. Maybe that would be a way. Let's move the camera down on. And let's look at all the different things that we see in this handout. So one thing we see is we should see the shear diagram, and another is the moment diagram. And those are very common expectations coming into the mechanics and materials class, is the ability to draw shear and moment diagrams. The next thing we see is something called the elastic curve. And the elastic curve is really what shape does this beam take when the load is applied and it is allowed to deflect. So this is really about the deflection. So this is the shape that it would take. And the deflection is the distance from the unloaded position to the loaded position. And over here on the right hand side, we see the word deflection, and then we see an equation for what this deflection is as a function of distance from the left end. and it's going to equal P, which is that concentrated load, over 48, E, the modulus of elasticity, I, the moment of inertia, times 3 times x, and that's this x is the distance from the left end, times L squared, that's the entire length, minus 4x cubed. So that would give you the deflection at any point from here to there, where we then have some symmetry, and on the other side it's just mirrored. You'll also see there's an equation here for the maximum deflection, and the maximum deflection would be here in the center, and that's PL cubed over 48 EI, and it's at x equals L over 2. So there it is. That's the deflection. For any one of these cases, we see the shear diagram, the moment diagram, the elastic curve, the equations for the deflections. There are other equations here for shear and moment and reactions, etc. Coming back. So we looked at the different loadings, a wide variety of different loadings, double check, and we looked at the deflection and the equations for deflection. Now let's talk a little bit about stress. So if I take one of those beams and maybe that beam we were just looking at, and we load it simply, and we want to know what the stress is at some location along the way. Maybe we take a look at the stress at this location. So I'm going to draw a free body diagram right here. We're going to talk about what would the stress be on the left-hand side of this beam. It's an internal stress. Now, when this deflects, what happens is the fibers on the top of the beam get pushed together, and the fibers on the bottom of the beam get pulled apart. So it turns out that the top of the beam is in compression and the bottom of the beam is in tension. If you take a popsicle stick and break it, and then just like this, just take it and break it, and you look in at the ends, you'll actually be able to see that the top fibers got pushed in and the bottom fibers got pulled apart. So then it turns out that as you go from compression to tension, you go through a 0 point. And the stress at this location is not the same everywhere on the cross-section. It's a compressive stress at the top fiber, and then as you start coming down, that compressive stress gets less and less until, I'm going to work on my focus here, until it's no longer a compressive stress and it's not yet a tensile stress, and it's got a 0 stress. And then once it goes through 0, it starts getting a little bit more and more and more until you have a maximum tensile stress. So the stress at this cross-section is different not only as you move across the beam from left to right, but as you go across the cross-section from top to bottom. And in fact, there's a midpoint there where it's 0. if this were a rectangular cross-section, that midpoint has a name. Well, it has a name whether it's a rectangular cross-section or not, but if it's rectangular, it would be in the center. It is called the neutral axis. And in the neutral, at the neutral axis, the stress is 0. So again, this is the bending stress. And it is going into or out of that cross-section. So it's perpendicular to the cross-section. So the bending stress is a normal stress, perpendicular to the cross-section. The equation for the bending stress is sigma equals my over I, where m is the internal moment at this point. So if we were using this case again, and it were this point, the internal moment there could be found on the moment diagram. So one of the values of the shear and moment diagram is it allows us to find the moment from left to right in a beam, or along the length of a beam. So if we just chose a point here, we could actually get the moment off of the moment diagram. So the moment is the same everywhere in this cross-section. It's different everywhere along the length of the beam, but when we choose a point in the beam, we choose this point right here, the moment is the same everywhere. So it's a fixed value in this cross-section. The moment of inertia is the moment of inertia about the neutral axis. And that is the same everywhere in this cross-section. But y is the distance from the neutral axis to whichever point we want in this cross-section. So if we're at the neutral axis, y is the distance to the neutral axis, well, it'd be 0. So the stress would be 0. The stress is 0 at the neutral axis. As you move away, the distance y goes up, so the stress goes up, until you get all the way to the outer fiber when y is maximum and the stress is maximum. So sigma is the bending stress. It's equal to m, the moment, times y, the distance from the neutral axis, over I, the moment of inertia. So there we have it. We've looked at a variety of different loadings. We now know how to calculate the stress using the moment of inertia, and the position in the cross-section. And we have equations that are provided to us for the deflection. That's it for bending video number 1.